We now state without proof two important results, which is on the Laplace transform of derivatives. Now these will be very useful when we try and solve, or when we demonstrate how to solve differential equations in the time domain by using Laplace transforms. So these two formulas are very important, and they can be remembered very easily. There are similar formulas for f triple dash t, f 4 primes, in fact for f n prime t. We will state the formula, but these are too important and will be most frequently encountered. First one states the Laplace of the first time derivative of the basic function, where LFT is capital Fs, is s times Fs minus small f naught. Again, the Laplace transform of the first derivative of time function ft is s Fs minus f of 0, where Fs is the Laplace of small ft. And when we take the Laplace of the second derivative of the basic time function, it is equal to s square times the Laplace of the basic function minus s times small f naught minus f prime naught. We have to observe very carefully that the Laplace transform of the basic function, whether in this formula or this formula, appears once only. The rest of the terms are all in terms of f naught, f dash naught, and so on. That is the derivatives of f naught, the basic function, evaluated for t is equal to 0. So these are the initial conditions that are imposed on ft. So for example, f naught will have a value which gives us the value of the basic function of time at t is equal to 0. Similarly, the first derivative of ft evaluated at t is equal to 0, and so on. Let us see how we can also apply this for some other purpose. Let us try and see how we can find the Laplace transform of, say, cos of at, given that the Laplace transform of sine of at is a over a square plus a square, or the other way around, given that the Laplace transform of cos at is s over a square plus a square, how do we get the Laplace transform of sine at? So let's see how we can use this. We'll write down the problem. We state the problem as using Laplace transform of sine at and the rule for derivatives, meaning Laplace transform of derivatives, find the Laplace transform of cos at. We will solve this problem and let us see how to go about this. The problem is using the Laplace transform of sine at, as of course we know that the Laplace transform of sine at is a over a squared plus a squared. We will use this result to find the Laplace transform of cos at by the derivative rule. We start by taking ft as cos at. Then f dash t is minus a sine at and f minus a square cos at. So we can write the Laplace transform of f double dash t, which is minus a square cos at. We write that as per the formula. Laplace transform of minus a square cos at, which is f double dash t, is a square fs. Fs is the Laplace of cos at minus s f naught minus f dash naught. Now, f dashed naught is nothing but minus a sine 0. So this has a value of 0. F naught, if ft is cos at, which we had taken, then f naught has a value of cos 0, which is 1. So this fellow has a value of 1. So we write down Laplace of minus a square cos at is a square fs minus s. Now this Laplace of minus a square cos at is minus a square times Laplace of cos at, which is fs. So this implies that minus a square times fs is nothing but s square times fs minus s. If we collect the fs terms on this side, we will get that this implies, you take this one here, s is equal to fs multiplied by s square plus a square. In other words, fs has the value of s over s square plus a square, which is a very familiar result to all of us. So this yields fs is s over s square plus a square, which we have done earlier as being the Laplace transform of cos at. So similarly, we can take ft as sin at, derive it twice and get a very similar result, which we'll do now, because this flavor will be carrying on and the process will become very clear. We'll change the problem. Now the problem is stated as using the rule for LT of derivatives, find the Laplace of sin at. How do we do this? Solution is take ft as sin at. Then f dash t is equal to a cos at and f double dash t is minus a square sin at. So we will apply the formula of the Laplace transform on the second derivative of this function. So we will write it on top. We have taken the function as sin at. Should not forget that. So since we have taken the function ft as sine 80, f naught is 0, f dash naught is equal to, see the f dash t is a cos 80, so f dash naught is a cos 0, that will be just a. Now we will apply the formula for second derivative. F double dash t is L of minus a square sine 80, and that is equal to a square fs minus sf naught. Sf naught means s into 0 minus f dash 0, that is equal to a. So we say that the Laplace of minus a square sine 80 is a square fs minus a. If we collect terms that have this fs here, minus a square Laplace of sine 80 is, other words, minus a square fs. So if you do a little bit of algebra, we will get, like the previous case, that the Laplace of sine 80 will be a over a square plus a square, which is also another very familiar result.